Hello, dear students, welcome to massive open online course on Swayam in chemistry. Myself Preeti Kiran, PGT Chemistry from Kendriya Vidyalaya No. 1, Air Force Station, Hindon. Dear students, in the previous classes, you have studied about atoms, molecules, atomic structure and electronic configuration. In Unit 4, Chemical Bonding and Molecular Structure of Class 11th, today you will study about Cossel-Lewis approach to chemical bonding, octet rule, covalent and electrovalent bond, formal charge, limitations of the octet rule. Now, chemical bonding and molecular structure. Matter is made up of one or different types of elements. Under normal conditions, no other element exists as an independent atom in nature, except noble gases. Most of these atoms exist as molecules, which are cluster or aggregates of atoms or ions of same or different elements having a distinct existence and its own characteristic properties. Obviously, there must be some force which holds these constituent atoms together in the molecules. The attractive force which holds various constituents like atoms, ions, etc. together in different chemical species is called a chemical bond. Since the formation of chemical compounds takes place as a result of combination of atoms of various elements in the different ways, it raises many questions. Why do atoms combine? Why are only certain combinations possible? Why do some atoms combine while certain others do not? Why do atoms have fixed combining capacity? Why do molecules possess definite shapes? To answer such questions, different theories and concepts have been put forward from time to time. These are Cossel-Lewis approach, valence shell electron pair repulsion theory, valence bond theory and molecular orbital theory. The evolution of various theories of valence and the interpretation of the nature of the chemical bonds have closely been related to the developments in the understanding of the structure of atoms, the electronic configuration of elements and the periodic table. Every system tends to be more stable and bonding is nature's way of lowering the energy of the system to attain stability. Cossel-Lewis approach to chemical bonding. To explain the formation of chemical bond in terms of electrons, a number of attempts were made, but it was only in 1916 when Cossel and Lewis succeeded independently provide logical explanation of valence, which was based on the inertness of the noble gases. The atoms of the noble gases, except helium, have 8 electrons in their valence shell. The valence shell electronic configuration of the noble gas atoms is, except helium, is Ns2 Np6, which represents the stable configuration and corresponds to the maximum stability. Due to stable configuration, the noble gases neither have any tendency to gain or lose electrons and therefore their combining capacity or valency is 0. Their inertness is so prominent that they exist as monoatomic gaseous atoms. All atoms other than noble gases have less than 8 electrons in their outermost shell. That is, they don't have stable electronic configuration. So, they combine with each other or other atoms to achieve stable noble gas electronic configuration. That is Ns2 Np6 or 1s2, which is the state of minimum energy and maximum stability. Atoms combine with each other only if the process leads to lowering of energy. Lewis depicted the atoms in the terms of positively charged kernel, that is, the nucleus plus the inner electrons, and the outer shell that could accommodate a maximum of 8 electrons. He further assumed that these 8 electrons occupy the corners of a cube, which surround the kernel. Thus, the single valence shell electron of sodium would occupy one corner of the cube, while in the case of a noble gas, all the 8 corners would be occupied. This octet of electrons represent a particularly stable electronic arrangement. Lewis postulated that atoms achieve the stable octet when they are linked by chemical bonds. In the case of sodium and chlorine, this can happen by the transfer of an electron from sodium to chlorine, thereby giving the sodium ion and chloride ions. In the case of other molecules like chlorine, hydrogen, fluorine, etc., the bond is formed by the sharing of a pair of electrons between the atoms. In the process, each atom attains a stable outer octet of electrons. Lewis symbols. In the formation of a molecule, only the outer shell electrons take part in chemical combination, and they are known as valence electrons. The inner shell electrons are well protected and generally do not participate in the combination process. G.N. Lewis, an American chemist, introduced simple notations to represent valence electrons in an atom. These notations are called Lewis symbols. For example, the Lewis symbols for the elements of the second period are as under. The significance of the Lewis symbols. The number of dots around the symbol represents the number of valence electrons. This number of valence electrons helps to calculate the common or group valency of the element. The group valency of these elements is generally either equal to the number of the dots in the Lewis symbol or 8 minus the number of dots or the valence electrons. Kossel, in relation to chemical bonding, drew attention to the following facts. In the periodic table, the highly electronegative halogens and the highly electropositive alkali metals are separated by noble gases. The formation of a negative ion from a halogen atom and a positive ion from an alkali metal atom is associated with the gain and the loss of an electron by the respective atoms. The negative and the positive ions thus formed attain stable noble gas electronic configuration. The noble gases, with the exception of helium, which has a duplet of electrons, have particularly stable outer shell configuration of 8, that is octet electrons, Ns2, Np6. The negative and the positive ions are stabilized by electrostatic attraction. For example, the formation of sodium chloride, that is NaCl, from sodium and chlorine according to the above scheme can be explained as. You can see the equation on the screen. Sodium gives sodium ion by losing one electron. The sodium has the electronic configuration with the inner core of neon 3s1, whereas sodium ion has the electronic configuration of neon. Now the chlorine, it gains the electron which is lost by the sodium and it changes into chloride ion. The electronic configuration, now you can see, it has achieved a stable electronic configuration of argon, that is 3s2 3p6. Sodium ion plus chloride ion now together form NaCl or Na plus Cl minus. Similarly, the formation of calcium fluoride CaF2 may be shown as calcium Ca losing 2 electrons and is changed into calcium ion with a stable electronic configuration of argon. Fluorine gains this electron and changes into fluoride ion. Now, fluoride ion has the inner core of helium with 2s2 2p6, the stable neon electronic configuration. Now calcium ion with a 2+ charge and 2 fluoride ions together form calcium fluoride, or Ca2+ and F with the minus charge. The bond formed as a result of the electrostatic attraction between the positive and the negative ions was termed as the electrovalent bond. The electrovalence is thus equal to the number of the unit charges on the ion. Thus, calcium is assigned a positive electrovalency of 2, while chlorine a negative electrovalency of 1. Causal postulations provide the basis for the modern concepts regarding ion formation by electron transfer and the formation of ionic crystalline compounds. His views have proved to be of great value in the understanding and systematization of the ionic compounds. At the same time, he did recognize the fact that a large number of compounds did not fit into these concepts. Now, the octet rule. Octet rule, Causal and Lewis in 1916 developed an important theory of chemical combination between atoms known as electronic theory of chemical bonding. According to this, atoms can combine either by transfer of valence electrons from one atom to another, that is by gaining or losing, or by sharing of valence electrons in order to have an octet in their valence shells. This is known as octet rule. Covalent and electrovalent bond. The Lewis theory was the first to explain formation of a covalent bond in terms of electrons that was generally accepted. If 2 electrons are shared between the 2 atoms, this constitutes a bond and binds the atoms together. For many lighter atoms, a stable arrangement is attained when the atom is surrounded by 8 electrons. This octet can be made up from the some electrons which are totally owned and some electrons which are shared. Thus, atoms continue to form bonds, single and multiple, until they complete an octet of electrons. This is called the octet rule. The octet rule explains the observed valencies in large number of cases. Langmuir in 1990 refined the Lewis postulations by abandoning the idea of the stationary cubical arrangement of the octet and by introducing the term covalent bond. The Lewis-Langmuir theory can be understood by considering the formation of the chlorine molecule, that is Cl2. The chlorine atom with electronic configuration with inner core of neon 3s2 3p5 is 1 electron short of argon configuration. The formation of the chlorine molecule can be understood in the terms of sharing of a pair of electrons between the 2 chlorine atoms. Each chlorine atom contributing 1 electron to the shared pair. In the process, both chlorine atoms attain the outer shell octet of the nearest noble gas, that is argon. Chlorine dash chlorine, that is a bond, the covalent bond between the 2 chlorine atoms. The dots represent electrons. Such structures are referred to as Lewis dot structures. The Lewis dot structures can be written for other molecules, also in which the combining atoms may be identical or different. The important conditions being that each bond is formed as a result of sharing of an electron pair between the atoms. Each combining atom contributes at least 1 electron to the shared pair. The combining atoms attain the outer shell noble gas configuration as a result of the sharing of electrons. Thus, in water and carbon tetrachloride, molecules formation of covalent bonds can be represented as. Thus, when 2 atoms share 1 electron pair, they are said to be joined by a single covalent bond. In many compounds, we have multiple bonds between the atoms. The formation of multiple bonds emphasizes sharing of more than one electron pair between two atoms. If two atoms share two pair of electrons, the covalent bond between them is called a double bond. For example, in carbon dioxide molecule, we have two double bonds between the carbon and oxygen atoms. Double bonds in carbon dioxide molecules you can see in the figure. Similarly, in ethene molecule, the two carbon atoms are joined by a double bond. C2H4 is ethene molecule and you can see the figure. When combining, atoms share 3 electron pairs as in the case of two nitrogen atoms in the N2 molecule and the two carbon atoms in the ethyne molecule, a triple bond is formed. Nitrogen molecule, you can see in the figure the triple bond. Ethyne molecule, again you can see the triple bond between the two carbon atoms. Lewis representation of simple molecules, the Lewis structures. The Lewis dot structures provide a picture of bonding in molecules and ions in terms of the shared pairs of electrons and the octet rule. While such a picture may not explain the bonding and the behavior of a molecule completely, it does help in understanding the formation and properties of a molecule to a large extent. Now, the writing of the Lewis dot structure of the molecule is therefore very useful. The Lewis dot structure can be written by adopting the following steps. The total number of electrons required for writing the structures are obtained by adding the valence electrons of the combining atoms. For example, in the methane molecule, there are 8 valence electrons available for bonding, 4 from the carbon and 4 from the 4 hydrogen atoms. For anions, each negative charge would mean addition of 1 electron. For cations, each positive charge would result in the subtraction of 1 electron from the total number of valence electrons. For example, for the carbonate ion, the 2 negative charges indicate that there are 2 additional electrons than those provided by the neutral atoms. For ammonium ion, 1 positive charge indicates the loss of 1 electron from the group of neutral atoms. Knowing the chemical symbols of the combining atoms and having knowledge of the skeletal structure of the compound known or guessed intelligently, it is easy to distribute the total number of electrons as bonding shared pairs between the atoms in the proportion to the total bonds. In general, the least electronegative atom occupies the central position in the molecule or ion. For example, in the NF3 and CO3 nitrogen and carbon are the central atoms, whereas fluorine and oxygen occupy the terminal positions. After accounting for the shared pairs of electrons for the single bonds, the remaining electron pairs are either utilized for the multiple bonding or they remain as the lone pairs. The basic requirement being that each bonded atom gets an octet of electrons. The Lewis representation of some molecules now you can see in the table. Now, I am taking few problems. Write the Lewis dot structure of CO, that is carbon monoxide molecule. The first step you have to follow is count the total number of the valence electrons of carbon and oxygen atoms. The outer valence shell electrons and the configuration of the carbon and oxygen atoms are 2s2 2p2 and 2s2 2p4 respectively. The valence electrons available are 4 plus 6, that is 10. Now, in step 2, the skeletal structure of carbon monoxide is written as CO. Step 3. Draw a single bond, one shared electron pair between carbon and oxygen, and complete the octet on oxygen. The remaining 2 electrons are the lone pair on carbon. This does not complete the octet on the carbon, and hence we have to resort to the multiple bonding. In this case, a triple bond between carbon and oxygen atoms. This satisfies the octet rule condition for both the atoms. Now you can see in the figure the octet of both the atoms is complete. Now I am taking another problem. Write the Lewis structure of the nitrite ion NO2 minus. It has a charge, a negative charge, which must be taken into account. So first of all, count the total number of valence electrons of the nitrogen atom, the oxygen atoms and the additional 1 negative charge equal to 1 electron. Nitrogen, electronic configuration 2s2 2p3. Oxygen 2s2 2p4. 5 plus 2 into 6 plus 1, total of 18 electrons contributed by nitrogen and oxygen and 1 negative charge. The skeletal structure of nitrite is written as ONO. Step 3. Draw a single bond, one shared electron pair between the nitrogen and each of the oxygen atoms, completing the octets on oxygen atoms. This, however, does not complete the octet on nitrogen if the remaining 2 electrons constitute lone pair on it. Hence, we have to resort to the multiple bonding between nitrogen and one of the oxygen atoms. In this case, a double bond. This leads to the following Lewis dot structure. Now, the next concept is the formal charge. Lewis dot structures in general do not represent the actual shapes of the molecules. In case of polyatomic ions, the net charge is possessed by the ion as a whole and not by a particular atom. It is, however, feasible to assign a formal charge on each atom. Let's define the formal charge of an atom in a polyatomic molecule or ion may be defined as the difference between the number of the valence electrons of that atom in an isolated or free state and the number of electrons assigned to that atom in the Lewis structure. The formal charge is the charge assigned to an atom in a molecule, assuming that electrons in all the chemical bonds are shared equally between atoms regardless of the relative electronegativity. When determining the best Lewis structure or predominant resonance structure for a molecule, the structure is chosen such that the formal charge on each of the atoms is as close to the zero as possible. The formal charge of any atom in a molecule can be calculated by the following equation. Fc, that is formal charge, is equals to V minus N minus B by 2, where V is the number of the valence electrons of the neutral atom in isolation in its ground state. Capital N is the number of the non-bonding valence electrons on this atom in the molecule, and B is the total number of electrons shared in the bonds with other atoms in the molecule. The counting is based on the assumption that the atoms in the molecule owns 1 electron of each shared pair and both the electrons of a lone pair. Let us consider the ozone molecule, that is O3. The Lewis structure of O3 may be drawn as, you can see on the figure that the screen, the ozone molecule is drawn. The atoms have been numbered as 1, 2 and 3. The formal charge on the central oxygen atom has been marked as 1. it is equals to 6 minus 2 minus 1 by 2 of 6, it comes to be plus 1. The end oxygen atom marked 2. The formal charge is equals to 6 minus 4 minus half into 4. It comes out to be 0. The end oxygen atom marked as 3. The formal charge is equals to 6 minus half into 2. It comes out to be minus 1. Hence, we represent ozone as along with the formal charges as follows. We must understand that formal charges do not indicate real charge separation within the molecule. Indicating the charges on the atoms in the lowest structure only helps in keeping track of the valence electrons in the molecule. Formal charges help in the selection of the lowest energy structure from a number of possible lowest structures for a given species. Generally, the lowest energy structure is the one with the smallest formal charges on the atoms. The formal charge is a factor based on a pure covalent view of bonding in which electron pairs are shared equally by neighboring atoms. Limitations of the octet rule. The octet rule, though useful, is not universal. It is quite useful for understanding the structures of most of the organic compounds, and it applies mainly to the second period elements of the periodic table. There are three types of exceptions to the octet rule. The incomplete octet of the central atoms. In some compounds, the number of electrons surrounding the central atom is less than 8. This is especially the case of the elements having less than 4 valence electrons. Examples are lithium chloride, beryllium hydride and boron chloride. Lithium, beryllium and boron have 1, 2 and 3 valence electrons only. Some other such compounds are aluminium chloride and boron trifluoride. Odd electron molecules. In molecules with an odd number of electrons like nitric oxide NO and nitrogen dioxide NO2, the octet rule is not satisfied for all the atoms. You can see from the figure. The expanded octet. The octet rule is also broken where atoms have an extra energy level which is close in energy to the p level. For example, elements in and beyond the third period of the periodic table have, apart from 3s and 3p orbitals, 3d orbitals also available for bonding. In a number of compounds of these elements, there are more than 8 valence electrons around the central atom. This is termed as the expanded octet. Obviously, the octet rule does not apply in such cases. Some of the examples of such compounds are PF3 that obeys the octet rule, but PF5 does not. PF5 has 10 outer electrons and uses 1 3s, 3 3p and 1 3d orbitals. Any compound with more than 4 covalent bonds must break the octet rule, and these violations become increasingly common in elements after the first 2 periods of 8 elements in the periodic table. Interestingly, sulfur also forms many compounds in which the octet rule is obeyed. In sulfur dichloride, the sulfur atom has an octet of electrons around it. Other drawbacks of the octet theory. It is clear that octet rule is based upon the chemical inertness of the noble gases. However, some noble gases, for example xenon and krypton, also combine with oxygen and fluorine to form a number of compounds like xenon difluoride, krypton difluoride, xenon oxyfluoride, etc. This theory does not account for the shape of the molecules. It does not explain the relative stability of the molecules being totally silent about the energy of a molecule. Now you can see the Lewis dot structures of many common compounds and molecules. Fourth step, the process is drawing the Lewis dot structure. Step 1. Arrange atoms into a skeleton molecule. Central atom of the lower electronegativity. The element written first in the formula is usually the central atom. Add up the valence electron of all atoms, draw single bonds and subtract electrons for each single bond from the total counted in step 2. Deal out remaining electrons, create double or the triple bond, satisfy octet rule, except for the hydrogen. Total electrons used in the Lewis structures should be equal to total valence electrons in step 1. Remember, while drawing the Lewis structures, hydrogen and halogens form single bonds. Oxygen family need at least 2 bonds to complete octet, so they form single or double bond. Nitrogen family need 3 bonds, so they form single, double or triple bond. Carbon family needs 4 bonds. Key steps to write Lewis structure. Now you can see the flow chart and the steps that will help you to write the Lewis dot structures. Just now we have studied that the Lewis structure was named after Gilbert and Lewis, who introduced it in his 1916 article. Lewis dot structure represent the molecular geometry and valence shell electrons of a molecule, also known as Lewis diagrams or formulas or symbols. Most useful for atoms and the molecules of period 2 and 3. It includes only valence electrons. The Lewis structures extend the concept of the electron dot diagrammatically, adding lines between atoms to represent shared pairs in a chemical bond. Lewis structures show each atom and its position in the structure of the molecule using its chemical symbol. Lines are drawn between the atoms that are bonded to one another. Pairs of dots can be used instead of lines. Excess electrons that form lone pairs are represented as pair of dots and are placed next to the atom. Dear children, so I hope that you have understood the concept of writing the Lewis dot structures and the octet rule. And you also understood that there are many exceptions to the octet rule and it's not universal. I hope you have understood all the concepts. Thank you.